Okay, for the second issue that given, right, we're given y squared plus 2xy is equal to a constant value. Okay, so the question asks you to find, okay, what is the axial velocity u equals to, and what is the velocity v equals to, right? So these are the information that is given to you. Okay, you're going to use this, okay, to find what is your u and v equals to.
I cannot use my phone now.
Okay, so how do we do this question? What are the important things that we know? Stream function is a function of what? X and y, right? What else do we know? A stream function is what? A constant value, right? So if you know that y squared plus 2xy is a constant, I think we can imply that the stream function will just be equal to y squared plus 2xy. Okay, so this is a very extremely important concept to check out. Okay, that you know that it's a constant value, you know that stream function is y squared plus 2xy. Okay, so with this, right, you can actually sort of be able to find what is your u and v already. Right? How do you find u? Is your psi over? Y. Okay, by the way, I think this is PSI, so it's psi. Someone point out to me, I think this is PSI. So for that psi. Okay, the other one, the middle is actually PHI, so it's fine. Okay, so anyone got the answer for you already? Okay, anyway, let's try this first. Okay, there's another way you can do this. So let's try to integrate this with respect to x first. Can we do that? How do you integrate our psi with respect to x? What do you have here? 2y dy dx, right? Then plus, this is a chain rule, right? Sorry, a product rule. Right, so what do you get from this equation here? You get 2y plus 2x dy dx, correct? Don't know what I'm talking about, right? Okay, let's try out. If I integrate, okay, first of all, you must remember, okay, this is respect to what? X and y, correct? Okay, now what we can do, right, is to do a proper differentiation. We mean to say, right, I can actually differentiate my phi with respect to x. So what do we have here? If you differentiate, okay, now if you see, right, this term here is your y squared, right? Does it have any x value? No, right, but you use chain rule. So in a sense, we can actually still differentiate this, so we can get 2y, but we must do a dy dx here. Correct? Okay? Now, for the second term, you have a 2xy here, so it's a variable of what? 2 times x times y. So we can differentiate x first, correct? Now, when we differentiate x, what do we have? We left with 2y. Right, but we can do a plus. Now we differentiate y, now what do we have? We have 2x dy dx, very good. Okay. Let me ask you a question. If I differentiate phi with respect to dx, right? What would this be? What's the numerical value of this? Anyone? Who thinks it's 0? Nobody? It should be 0, right? Why? Because, yes, phi is a constant, so it doesn't change with respect to space. So this will be equal to 0 here. Anyone got any issue with this differentiation here? No, okay, good. Okay, so notice what I'm doing, right? I'm not doing a partial derivative. I'm doing a proper differentiation here. That's why I put a capital D here. Okay, there's a reason for this. Okay, why? Because how is dy dx related to v and u? Can you guys remember? A few slides before, right, I sort of give you an equation, right, where I say dy dx is equal to something. V over u, very good. Okay, so right, we can actually now we have this equation which I just differentiate for you. Okay, so what I can do, right, is to make dy dx my subject. Okay, so I put dy dx together. Okay, the rest, right, I put on to the left hand side here. Okay, I'll get this equation here. Okay, so if you guys can recall, okay, my dy dx is equal to v over u. Okay, I can actually know that my v over u equals to minus y over y plus x. So v can be negative y, and u can be equals to y plus x. So how do you know whether your answer is correct? Very simple, okay, because in the question you're given what? The velocity magnitude, right? Okay, is equal to what? The square root of x squared plus 2xy plus 2y squared, correct? So how do we find, now if you're given this v value and u value, right? How do you find the magnitude? You just take y squared plus y plus x squared, right? Are you following me? Okay, so when you do that, right, you can check this answer already. You can approximate it. Okay, so this is just for you to check whether the answer is correct. Any question? Yeah. Okay, so this is the final answer, right? But just for you to do a cross-reference check, you can actually do this. You should get the same answer as what the question is given to you. Right? Okay, so this is just an example of how you can make a stream function. But during your potential flow theory, right, when you do all the source, sink, and so on and so forth, right? Okay, the stream function is more important, so we'll come back to that later on. Okay, can I just move on? Okay, so far, right, we are just looking at streamlines. Okay, that means you're going from left to right or bottom to up. Okay, but obviously, if you have a fluid flow, okay, there's this thing called rotation that you must consider. Okay, most of the flow that you can see, right, if you just burn an incense, right, the smoke that's coming from the incense is not a straight line, right? There's a lot of vortices and things, so it actually rotates. Yeah, so we should also be able to quantify what is this fluid rotation that we're looking at. Okay, so when there's a rotation, okay, how do we quantify rotation? Okay, anybody know? If I move on a straight line, right, my velocity is my velocity, right, linear velocity. But if I move in a rotational motion, what kind of velocity do we have? Angular velocity, right? Correct? So when we have a rotational motion, okay, we actually can quantify that by using this thing called omega. So omega represents your angular velocity. Okay. So a linear velocity is a vector quantity, okay, because it's x, y, and z. Obviously, right, for angular velocity, it will still be a vector quantity. So you can actually express your omega as omega x plus omega y plus omega z, okay, in the three directions that we're looking for. Okay, how is omega expressed? Okay, we can actually express this in terms of this thing known as the velocity gradient. Okay? So what is this term here? Anybody can recall? Anyone? It's in your lecture one, the last slide that I gave to you before I go. Right? So this is actually what somebody just shouted, yes. This is a curve of your velocity vector. Okay? So you all must embrace this. No choice. Okay, you'll be using this a lot also. Okay, so let me just explain to you what does all these terms mean and the significance of this. So I, j, and k represents the x, y, z direction, right? Okay. Now what is delta y? Okay, for example, what is delta u over delta z, delta p over delta x? What are these terms called? What do you know these terms as? They are known as what? Your velocity gradients, right? Because we always think that gradient is respect to time, but actually it's not. It can also be respect to what? Space. Remember in the Lagrangian that we talked about, that a flow field can be respect to space and time, right? So this tells me, right, my u velocity can be respect to z, can be respect to y. Okay, my v velocity can be changing with respect to z, can be with respect to x also, right? So these are all known as velocity gradient, all right? So these are very important, okay, because this tells me, right, how does the three dimensions, the three velocities that have u, v, w changes in space. Okay, because if there's a change in this direction, right, because if you notice here, u doesn't change with x here. Why? Because if u changes with x here, right, it's just your local acceleration in the same direction. But I'm not concerned about that. I'm concerned about how does u change, right, in the other two directions, my y and my z direction. I'm concerned about how does my v change in x and z direction. Okay, and same for w, right? I'm concerned about how does w change in terms of x and y direction. Because when you change in opposite direction or different direction, there's a shear force. When there's a shear force, right, it causes a rotation. Right? So that's why we're looking at velocity gradient, not in the same direction. Okay? Understand what I'm saying? Almost like material, yeah, you're right. It's always about it's sharing of forces. That's why there's rotation. Okay, so that's the first important thing that you must know. Okay, all these terms here are known as your velocity gradients. Okay? Second thing that's important is this. Okay, when I look at the I component, that means when I look at the x component, okay, the vectors inside here, okay, cannot have any x component inside. It's only my w and my v's, okay, and my y inside. Okay, this is how you can memorize also. In my j component, I cannot have any y values or v values. It can only be my u, my w, my x, and my z. Okay, and then for k values the same thing. Okay, you cannot have any z value or w value, it's only my v and u. Okay, now what is the mathematical implication? It means, right, this term here, okay, is always normal to I. This term here is always perpendicular or normal to j. This term here is always normal to k. Are you all following me? Okay, what does this mean again? Is this when you talk about curl, right? What's the meaning of curl? That means you're taking two vectors cross multiply, right? Now, if I have two vectors x and y, right, I do a cross multiplication. What do I get here? So this vector is always perpendicular to this vector here, right? So that's why you can see from here, right? When I do my curl, okay, when I look at the I component, it's always this value is always perpendicular to the I component. Right, so you're always looking at the normal component, okay, for every term here, wx, wy, wz. Okay? So a curl of a velocity vector always is equal to half of the curve here, which is equal to your angular velocity. Okay? So when we talk about rotation, there are two quantities that we can quantify rotation. One is angular velocity, okay? The other one is this zeta, okay, which is your vorticity. Yeah, Z-E-T-A, I'm very sure it's zeta. Okay, so zeta, right, represents your vorticity magnitude or your vorticity value. Okay, so this is a new word for you. Okay, that's where we get things like vortex, vortices. Okay, the quantification of these two is called the vorticity. Okay, which is your zeta here. Okay, so vorticity, zeta, is always 2 times of your angular velocity. So that is always 2 times omega. Alright, so that's why zeta is supposed to be here. Alright, so if I write from a math function point of view, right, zeta is basically just the curl of my velocity vector. Okay, so if, right, my zeta is equal to 0, okay, I can just say that there's no rotation. So if there's no rotation, we call this as an irrotational flow. Okay, and if it's an irrotational flow, it just means that the flow is purely translational, x to y, x direction or y direction. Okay, there's no rotation involved. Okay, we all good? Okay, so if you can also recall what I've done in the first lesson, right? I told you guys when we talk about lift of an aircraft, right? Last time the part we talked about the drift equation, correct? Then I mentioned this word called Kutta-Joukowski theorem. Can you remember this word? Okay. So when I talk about Kutta-Joukowski theorem, right, I told you guys that in actual fact, right, lift is a function of your circulation, right? So therefore, right, when I talk about fluid rotation, besides angular velocity and vorticity, the last one that's important actually is this thing called circulation. Okay, circulation is very simple. It's just meaning, right, how does a flow circulates around a blood body or a solid object. Okay, so this is the most important rotation concept that you must know. Okay, because this will link us to the Kutta-Joukowski theorem. Okay, this will also link us from potential flow theory right into 2D airfoil theory. So this is extremely important. Alright. So what is rotation here? If you want to visualize rotation, really just this. You have an airfoil. Okay, a flow goes from left to right, but if there's a presence of rotation, right, I can actually decompose the flow into two flows. One is an axial flow, alright, one is a rotational flow. That means it's moving around the solid body that I have. Right? So how do we quantify, or how do we actually measure the value of circulation? Okay, if I write this in words, okay, it's just the line integral, okay, of the tangential component of the velocity. So tangential means, right, if I'm rotating around this direction, so this is a clockwise direction, okay, all the tangential velocity. If you can imagine, right, I have a flow that's rotating, right, okay, if I want to find, let's say the velocity at this point, I look at the tangential velocity. If I look at this point, I look at the tangential velocity. Okay, if I want to look at this point, I look at the tangential velocity. So that's why we call this as tangential velocity component. Yeah. But for simplicity's sake, right, I don't look at anywhere else except the x, y. That means the left side, right side, top and bottom. So it's easier for us to visualize this. Right. So understand what I'm saying? No. Okay. When I talk about tangential velocity, right, okay, it's just telling us that the flow is always rotating in this direction. Okay, so tangential of a circle means, right, if I, let's say, look at this point here, the tangential velocity is this. Correct? If I look at this particular point, the tangential velocity is this. Correct? If I look at this point, then it's this direction. Agree? Okay, so I can actually think about this, right? Everywhere along any point, okay, I can actually find the different tangential velocity that I want. Correct? Okay, so but you can imagine, right, the more points I have, right, the more accurate my answer will be. Correct? So for us to actually simplify this calculation, the better way for us actually is to do an integration. That means we are looking at a summation series here. Okay? So this integral is like what we have been doing. Just that we put a line, a closed circle here, right? It's known as a line integral, a closed integral. That means I'm looking at everywhere around the block body here. Okay, V here represents your velocity vector. L here represents the length scale. That means, right, if this is a square box, okay, that means it's a parameter of the square. If this is a round shape, okay, then what will it be equals to? Circumference 2 pi r, right? Okay, then repeat that. This dl represents the parameter of where the flow is passing around. If the question gives you a square box, basically it's just the parameter of the square box. If the question gives you a rectangular block, it's just a rectangular parameter. If the question gives you a circular shape, which most of the time is a circular shape because it's circulation, right? Okay, that means you're looking at the circumference. Okay, that's why it's a dl here. Okay, so this equation here, okay, represents this flow here where there's a circulation in this direction. Okay, that's why there's a negative sign. Why is there a negative sign? Okay, because by convention, okay, most of the time when we have a clockwise circulation, we consider it as positive. Right? So in this figure here, okay, because it's going in this direction, okay, that's why it's anti-clockwise, that's why we put a negative sign. Is everybody okay so far? Okay, yeah. Okay, so let's try to understand this equation a bit further. Alright. So notice there's a dot product here. Okay, velocity vector is a vector. Velocity is a vector. Displacement is a vector or scalar? Displacement, I mean the length scale around this, is it a vector or scalar? Scalar or vector? It's a vector, right? Because either I go from right to left or I go to left to right. Displacement is a vector, right? You go from clockwise or anti-clockwise, right? It's a vector quantity. Yeah. So this is a dot product of two vectors. What do we get at the end of the day if we have two dot a scalar answer? Okay. Anyone got any questions here about this? Okay. Okay. So we can then expand this out because what's the velocity vector composed of? My u direction, my v direction, my w direction, right? What is my length scale composed of? My x, y, and z. So I can actually expand this out into this form. Okay, I do a dot product. Okay, I get my u dx, v dy, and w dz. Are you all good with this? Okay. Because u times dx, v times dy, w times dz. Okay, that's where you get this answer here. Okay, so we need to maybe perhaps understand this a bit further using this diagram here. Okay, so let me just try to my level best to explain this to you. Okay, you have a box here. Now, what does this box represent? A control volume. Okay, inside this control volume, okay, we have a certain velocity in the center here. Okay, your u and your v also. Okay, in this diagram, you are given some dimensions. From a to b is dx. From b to c is dy. Alright. So let's, for example, look at this particular arrow here. Okay, what is this velocity equals to? If in the center, okay, I have got a v velocity here. Okay, how is this velocity related to the velocity at the center of the control volume? Are they the same or they'll be different? They'll be different. Okay, because my velocity as I go from left to right, or from center to right, or from center to left, okay, there's a certain change in answer. So how is this related at this center point to this point? Okay, it's given by this equation here. Okay, you have your velocity v at the center, okay, plus by the change from dv to dx. Because if I want to look at how v changed in the x direction, it will be dv over dx here. Correct? Now, the distance between this center point to the edge of this box here is dx over 2. Okay, that's why I got my dx over 2. Okay, this tells me the velocity at this point in relation or respect to the point at the center here. Okay, so if I do the same thing, if I want to find the velocity here, what do you think the answer equals to? Yeah, it will just be v minus dv dx plus dx. Okay, so we can do likewise, for the top, okay, and also for the bottom here. All right. Now, why is this important? Okay, because if you notice, from this integral here, we have our u dx, v dy, and w dz. Okay, so we can actually further simplify this equation here. So, how do we simplify? Let's assume, this is a two-dimensional figure. Okay, so what happens if it's two-dimensional? What in this term will be cancelled out? Okay, so this will be cancelled already. Alright? So, you think about this, I can actually find u dx for this particular location, okay, my v dy for this particular location. So basically, instead of having this closed integral, okay, I'm trying to add up all the terms here. Okay, so I can remove this integral sign. Like what of your friends say, integral means summation. So I'm just summing up this value, this velocity here times dx, plus this velocity here times dy, plus this velocity times dx, and then plus this velocity times dy. So I'm just expanding the terms out here. So when I expand the terms out here, okay, this is what I will get. This term here, u minus du dy times dy dt over 2, is this term here. Yeah, I times by dx. Okay, now this term here is for which one? This v plus dv dx times ds over 2 times dy is which one? It's on this one, right? Okay, that's why, the next term here, it has to be a minus sign because I'm going in a anti-clockwise direction, right? So because this is pointing in the left to right, but when I do my anti-clockwise, it becomes right to left. This is a negative sign. Okay, similar for this when I go down here, Okay, so my circulation is in this direction here. That's why you have a negative sign here. Okay, so the beauty of this is this. I actually have this closed integral which I cannot solve, but because I actually put in some values here, I expand the integral into a summation of 4 terms here. My bottom, my right, my top, and my left. Okay, when I do this right, many of the terms here will actually cancel off. Okay, the final answer, if I were to just show it to you, okay, it will just be equal to this. Okay, because many of the terms are the same, okay, and they will cancel out. Alright. This unfortunately is also quite important. You might want to be asked to derive this equation also. Okay, so need to derive this. Okay, so somebody asked me this before, last year. Okay, if right, this is not dx and this is not dy, for example, okay, then if I give this as 2dx and 2dy, will I get the same answer? Or will I get a different answer? I'll get the same answer. Okay, because it's just a dimension here. So for this case, right, the book just used a very simplified, just dx and then just dy here. Right, so as long as the dimensions are consistent, okay, the final answer will be the same. Right? So this is a very important equation. Okay? Why is this important, right? What does this term represent to you? Anybody can know what this equals to? Okay, look at this equation, right? And look at go back to this side. Look at this equation here. Any terms here equals to this equation here. What is this equals to? Anyone? Omega x, omega y, or omega z? Omega z. Very good. So this is actually my omega z here. Yeah. So just now, right, we say, right, vorticity is 2 times your angular velocity, correct? This tells me, right, my circulation is always equals to my angular velocity times by dx dy. Okay? That's the first thing. Second thing is this. This is omega z, right? Okay? Now this is what? X and y, right? So that means, right, this omega z component is always perpendicular to my dx and my dy. Okay? Now what is dx dy equals to? What is x times y equals to? Area. That's your dA here. Okay? So this is really just your curl of the velocity vector. So why is this important? This is important because, right, I actually now have a different definition for my circulation. Just now, right, the definition for circulation is what? The velocity times the length scale, right? You do a closed integral. Now, what is this equation telling me? Circulation can also be equal to what? The normal component of my vorticity or my angular velocity multiplied by the area that I'm looking for. Okay? So if I write this in words, right, it just tells us that circulation can be equals to either, okay, the closed integral of my velocity multiplied by length scale, or it's equals to the curl of the velocity vector multiplied by the area that I'm looking for. Okay? The very important thing that you must remember is this. The angular velocity here is always perpendicular to dx dy. Okay? So if I ask you to expand this out, right, for example, if now I have dy dz here, dy dz here, what will this component equals to? Okay, if I have dy dx, sorry, dy dz here, sorry, what will this equals to? Omega x. Okay, so you have dz dx, what do you have here? Omega y. Okay, so it's always perpendicular to y, right? So why do I do this, right? It's because this is known as a very famous Stokes theorem. Okay, if you look at all your exam questions, question 2A has one. Okay, so question 2A requires either when they give you the angular velocity, right? Okay, they will ask you to find the circulation, or they give you the velocity vector to find the circulation. So both ways work together. As long as you're given one component, you can actually find the other components, right? So this is extremely important. Okay, so if I write this down in words, right, it just tells us that the surface integral of the normal component of the vorticity is always equal to the line integral of the velocity vector around the length scale that we're looking for. Okay, so more specifically, right, the normal component, right, in vector form, okay, we run on this n value here. So n always represents the normal component. Okay? Are we all good? Okay. So you learned a few things that's important today. Stream function so far, okay, which is part of the potential flow theory. Second thing you learned, which is on circulation. Okay, in particular, right? Okay, if you can understand the Stokes theorem, okay, the whole circulation concept you have understand. Right, so please go and try to derive the equation yourself. Okay, if you cannot, kind of see me also. Alright. Okay, so when we talk about vorticity and circulation, right, the question that you should ask me is this: what causes circulation? What causes radiation? Alright. So the very simple way to actually answer this question is this: when you look at this airfoil here, okay. So as what I say, right, the idea for us is to make this flow as laminar as possible, right? But the thing is, right, as your flows Reynolds number increase, okay, there's a tendency for the flow to separate away from the surface. And when the flow separates, right, okay, there will be this thing called turbulence here. Yeah. Now, what causes the turbulence here? Okay, the turbulence is caused by this thing called shear stress. Yeah. When you have a shear force, right, okay, you have a velocity gradient, your du dy, your du dz. Okay, when there's this velocity gradient, okay, it causes the rotation to happen. Right, so that's why shear stress is very important. So this, in essence, right, really is just this thing called a boundary layer. Okay, one of the best ways for us to understand this, right, is using a boundary layer theory. Okay, so this is a wing. Okay, let me try to explain this to you. You have a flow that's coming in here. Okay, so when it hits the leading edge of the airfoil, at this point here, we always call this a stagnation point. Okay, what does it mean when we talk about stagnation point? Anyone? What is equal to 0? Velocity equals to 0, right? What is maximum here? What is maximum here? Your pressure is maximum here. Okay, so if you do a CFD calculation for me, right, you realize that the P value here is always maximum. The V value is always equal to 0, okay, because it's a stagnation point. Okay, so once the flow hits the surface of the leading edge, right, okay, it starts to move two ways. Okay. Right, you go to the top and you also go to the bottom. Okay. Now, if I want to look at the boundary layer, the boundary layer, right, is not so big, in the sense, this is just elaborated for you guys to see. A boundary layer is actually very thin. Meaning to say, right, I cannot see by the naked eye. Yeah, it's actually, let's say, for example, this chord length is, I don't know, 3 meters, for example. Alright, the boundary layer is probably like 0.1 millimeter, or even the most is about 1 millimeter. So it's very small with respect to the chord length. Okay, but it's very important because this is the fundamental fluid mechanics, right, where it causes things like turbulence, drag, and so on and so forth. So then, therefore, right, we need to be able to understand how does this flow, right? I'm sure Prof. Simon will say something on this. I'm sure.
Probably
Say again.
probably ask us to do an example about ourselves.
Oh. He's, just a bit of history. Prof. Simon, I think his PhD or whatever is also on boundary layer. So he should know this very well. My PhD is also on boundary layer. So it took me 4 years to understand what's a boundary layer. So I don't expect you to understand boundary layer today. But in essence, right, next year you all need to understand this. You all need to try to understand this. But so in the boundary layer, right, okay, like what I said, from this aerospace journal, right, you want to have a natural laminar flow, right? It means, right, I don't want to have any of these turbulent structures here. Okay, because, right, let me just repeat, okay, when the flow starts to detach away from the surface of the airfoil, okay, this is where turbulence occurs. And when there's turbulence occurring, right, there's this thing called induced drag. So there's drag, right, you don't like drag, right? So we want to reduce this. So the idea is this: what this book or this Airbus book is trying to do, right, is to have a laminar boundary layer as much as possible all the way to the downstream. Okay, but in the typical airfoil, right, okay, because you're moving at very high speed, the flow have no choice, right, but to separate away. Alright, so you will see that the flow, right, goes from a laminar flow, and then as it accelerates, right, okay, it comes to a point here where there's this thing called transition. Okay, so what does mean of transition means? It means, right, the flow starts to separate away from the surface of the wing. Okay, the moment the flow starts to separate away from the wing, okay, then you have this thing called a turbulent boundary layer. Right? So because when there's turbulent boundary layer, right, okay, your flow starts to rotate. Your flow starts to rotate because of this thing called shear stress. And when your flow starts to rotate, okay, you have, let me just go back to this, you have all this, You have all these values here. Your delta y, delta z, all these terms, right, which is your velocity gradient. Okay, and because of that, right, that's why you have rotation. Alright? Okay, so you can see from here, right, every flow that we have, right, always starts from a stagnation point, okay, to a laminar boundary layer, eventually, right, to this thing called turbulent boundary layer. Alright, so from a concept point of view, right, if anybody asks you this question, what causes a turbulent boundary layer, you must always say, right, a flow always starts from a laminar flow, a laminar boundary layer. Okay, then it starts to separate. Okay, that means the flow is detached away from the surface of the air void. Okay, this is called the transition period. Okay, and then eventually, right, it will become a turbulent flow. How do we quantify this, right? The next lecture, I'll show you how to quantify this. Okay, when you are supposed to find the skin friction drag. Okay, that means because when there's turbulent flow, there's a certain drag induced, right? You can quantify that value. Okay, so you realize that a laminar drag versus a turbulent drag, right? The turbulent drag is always so much higher than a laminar drag. Right, so we'll be able to quantify. Yeah. So when you see this, right, what are all these little shapes here? You know, like you have a curve, you have a curve, you have a curve, right? These things are actually called your velocity gradient. Okay, what is a velocity gradient? It's actually your du dy. You see here? Okay, u, right, represents what flow? The axial velocity, right? Now, what is y? Y is in the x direction or y direction? Y direction, right? So that means u is perpendicular to y. This actually is always called as a strain because it's a shear force, right? Du dx, right, doesn't give you a shear, right? Because u and x in the same direction. It just give you a force, correct? But du dy gives you a shear. Because one is in this direction, one is in this direction. So therefore there's a shear. Alright, so this is your du dy. So when I talk about du dy, right, it's just a two-dimensional analysis. If you can appreciate, right, if I go to three-dimensional, I got my dw, dx, so and so forth. Okay, so du dy represents all these little velocity profile. Okay, so some people call this as velocity gradient. Okay, some people call it as your velocity profile. Both are the same thing. Alright, just telling us how does my u changes away from the surface of the air void. Okay. Okay, so this diagram here that I have set for you, actually is also on top here. Okay, so just have a few important definition. Y is always the distance away from the wall. Okay, that means when you're nearest to the wall, your y is equal to 0. Okay, as you go further away, right, your y will increase. U represents the axial velocity, right? So you can see, right, nearest to the surface of the wall, because there's drag, there's friction, right? What is my u equals to? What will it be equals to? 0, right? But furthest away from the wall, right, it will reach the friction value. That means furthest, no friction force involved. Okay, it will just be as is. Okay, the velocity at one. This whole thing is known as your du dy, which is your velocity gradient. Okay, some people also call this as the boundary layer thickness. How thick is the boundary layer? Yeah, because you can imagine, right, the flow will have this profile, right, but as it goes away from the surface, right, it's just going to be a straight line. Okay, it's just a friction velocity. Okay, so one other important concept is this. Just now I mentioned, right, at the surface of the wall here, okay, the speed is equal to 0. Why? Okay, because it is known as the no state condition. Okay. Okay, there's a no state condition. Okay, it will cause the fluid or the air, okay, to stick to the contact surface. Alright, that's known as the no state condition. Right? Are we okay? Okay, so I've covered stream function, rotation, okay, a little bit on boundary layer. Okay, so the last thing, or not last thing, second last thing I must cover with you guys, right? Okay, is this. Under the potential flow theory, there are two important variables that you must consider. One is your stream function, okay, known as PSI, psi. Okay, the other one that's important actually is your velocity potential, which is your phi. Okay, now how are these two related? Actually, very simply put, right? okay, your stream function, okay, is always orthogonal to your velocity potential. Okay, when I say orthogonal, right, it means what? 90 degrees. Okay, so you can see, right, your stream function, if it's going in all this direction, your velocity potential, right, will be 90 degrees to it. Okay? Later I will show a picture where you superimpose both together. But for now, right, okay, let's go back to the very simple assumption now, okay, where we say there's no rotational flow. So remember when we say if it's an irrotational flow, okay, your angular velocity will be equal to 0. Okay, therefore, right, we can say that the term that we have, the z term, the omega z term, should be equal to 0 here. So the dv dx minus dv dy should be equal to 0 here. Okay? Now, how do we relate? Just now we relate u and v to your psi, right? Your stream function. Okay, so for this case, we also must relate our u and v to our phi. Okay, our velocity potential. Alright? So how do we do that? Okay? Can I move on? No. You can copy this.